Hello, Eric here from Laserscanning TV, company Laserscanning Europe, and I'm again here with Janis. And Janis, what we speak about this episode?
Yeah, hi, I'm Jannis, and we did a accuracy test. Last time in the video, we had the little one, the K1, and today we are speaking about the accuracy of the L2 Pro, the bigger version from XGRIDS.
I can say this, we got really amazing results out, and if you are not like to miss this, then stay tuned. Before we really make a sharp start here, maybe you tell something about your person and what you done.
Yeah, hey, I'm Jannis, and I'm studying geomatics at the State University of Applied Science in Dresden in Germany. I'm now in the sixth semester, and yeah, I did some accuracy testing about the L2 Pro, which we can see here on the right side. The scanner has a range about 0.5 to 300 meter. It depends on the version of the scanner. I use the 16 channel scanner, and its scan frequency has 320,000 points to 640,000 points. And yeah, we got a camera resolution about 48 MP. And yes.
Yeah, I think maybe I precise this. Also, we use the 16-channel version of Lixel L2 Pro. It is definitely in a size system, and this have then the range from 120 meter. So this is this is the smaller version from the big scanner, and have the speed from 320,000 points per second. So now we can go forward.
Let's come to the two softwares from XGRIDS. On the left side here, we have the Lixel Studio. It's a program for processing point clouds. And on the right side, Lixel Cybercolor. It's a software which creates photorealistic 3D models based on the 3D Gaussian splatting. And therefore, I got a video which shows our test field for the indoor. And yeah, here we can see we can switch from to the point cloud, and we can move freely in this model. And yeah.
Yeah, I can say that the XGRID become super famous for their. I think there was one of the first scanner who have a very good Gaussian splatting implementation. I think their system runs very famous for this. But of course, the big one is the real measurement system, not only an optical or a virtual system. So, and then let us start with the measurement options from the system.
Yeah, it was my task to check the geometry accuracy of the L2 Pro. And for that, I did some accuracy testing for indoor and outdoor applications. The test field was a hall in the HTW Dresden, so the hall that we see in the previous video. The first task was to check the change in room distances after processing with and without crowd control points. The second task was a comparison of the point cloud of the L2 with the point cloud of a terrestrial scanner, the Faro Focus. And the last task was the accuracy verification in outdoor settings. Here we can see our test field and its extensions. The hall is also used to calibrate laser scanners. That means it's got many control point markers with highly precise coordinates. And you can see the crowd control points, which were used to reference the scans, and the local coordinate systems. These are here, these 4 green points.
Maybe it's important to say that this is a very stable facility. So it's a big concrete facility. I think originally they developed this to. I think the basic idea in the beginning was to put there some locomotives inside. So and then later they don't have these various stuff in the university, and then they make it them for the mechanical engineers. Actually, they're using this, and the surveyor occupied the whole structure to put there a lot of markers inside, and this building is super stable against vibration, and also I think the climate control is also pretty good inside of this building.
Yeah, so let's come to the aim of my study. It was about testing whether the geometry of the point cloud is improved by using ground control points and a comparison with the terrestrial point cloud of the Faro focus, and also the verification of outdoor accuracy. So my process was the data acquisition with the L2 Pro, the data processing in Lixel Studio, with and without ground control points, and the data evaluation. Yeah, here we can see it's about the distance comparison between the control points. Here in the upper right corner, we can see where control points are located. I use the control points from Faro, and I calculated the spatial distances between the control points using the given coordinates. I then carried out measurements in PointCab by creating sectional views, measuring the middle of the control points and calculating the distances. And a total of 15 differences were used between the control points. And the distances were between 2.8 meter and 40 meter. And yeah, here on the bottom, in the middle column of the chart, we can see the value of the deviation from the target distances of the process point cloud without the influence of the ground control points. We can see here 9.2 millimeters. And on the right side, you can see the difference to the point cloud processed on the basis of ground control points. And there we have 5.3 millimeters. And the result is that we improved by using ground control points about 4 millimeters.
Okay, yeah, that's interesting that we have an improvement from 4 millimeter, and actual also the absolute value from 5 millimeters and 9 millimeters are super good. I have a question. If I look on the picture, there's also some control points. There's market under the roof. Was there also checkerboards there in the middle here from the picture? They are directly under the roof placed in the hall, like this one and the other ones?
Yeah, we got some up here, and yeah, they are placed everywhere in the hall.
Okay,
So, yeah.
but it's hard work from the university to place them there. So I think you need some elevator to touch their point. So
I think so too.
I think audience can see that it's a very good test field. So not only some points on the side, so everywhere.
So let's come to the software CloudCompare. It's an open source software for processing point clouds, and I use the software for a comparison of the terrestrial scan data Faro Focus and the L2. And for this purpose, I put both point clouds on top of each other. Then I use the function cloud-to-cloud distance, which makes differences visually easily recognizable. And yeah, the reference point cloud was the point cloud of the Faro Focus, and the compared of the L2. And the compared one, that's the one which the distances are calculated. So CloudCompare calculates distances of the individual points relative to the reference cloud. And the generated scalar field is placed in this cloud. And here on the right side, you can see the color scale with the distances. And here's a video which you can see the coloring of the distances to the reference cloud. And here we can see how the distances goes up. And we can see that most of the differences are in the range of 3 centimeters. So nearly the whole hall is colored in blue. And we have nearly 0 green and orange areas. And here, when it comes to the end, we can see some red areas. I think that are areas here, like we can see that's a door or this I think, movable objects such as a crane or something like that. And the point cloud of the Faro-Focus was taken, I think, more than 1 year ago. So in the hall, there can be changes here. So here we have some other views from the side, the top and the bottom.
Yeah, I think it's the side view. You see there's these red areas as the doors and the crane area, and in the bottom we check these areas out, but in the inside there are, I think we have shown this on the video, there are some mobile, what you would say them, some cells where robots are placed, and we imagine that we scan there through any fences or like windows, what was there, like I think they have fixed walls, and inside of the walls are some glasses, so I think we can see that the red areas on the bottom line coming from these objects where we scanning through other materials, but we can see everything is below the 3 centimeter what XGRIDS offer in their tech sheet.
Yeah, that's right. So I also did a more detailed color scale. Here we can see how it's done. So
yeah, I think
more narrow steps.
Narrow steps. Yeah, I think I can explain it. So I think we say, okay, we are under 3 centimeter. Everything after our first check of the data, and then say, oh, let us do it new, because few manufacturers offering and say we have SLAM scanner with 5 millimeter accuracy. Say, let us take this if we can achieve 5 millimeters, and then we take the next step and see then from 5 millimeters to 1.5, because we in Europe, we have often the rule there's a 3D model, or a 2D drawing should be better as 2 centimeters. So if we can then spend maximum 1.5 centimeters, then we have 5 millimeters for generalization in drawings. And then finally you can take from this original point cloud and 3D model. This was the shift what they have, also 5 millimeters, what the best say they have, 1.5, this next step, and then we go further the next steps. So 3 centimeter is that's what XGRIDS offered to the client. So yeah, let us move forward. I'm very interested.
Yeah, I also got a video where we can see how it's colored. And we can see most of the areas are colored in blue and in green. And here we got some yellow. Maybe we can skip a little. Yeah, and we can see mostly of the area are colored in blue and green, and that means that the hall has only deviations. The most of the hall has only deviations up to 1.5 centimeters.
And that's very interesting. I think maybe let's move to the next slide so we can see it also. As a blue means below 5 millimeters. Also there's many areas there under 5 millimeters. Then we have all the greenish part, what is up to 1.5. And then we have a little bit interesting here in the side view, the small area with the yellow part, but yellow can be from 1.6 centimeters to 3 centimeters. So that can be super close to these 1.5 that we actually not can say to people. And then we see the red areas like we saw before where we have these movable objects inside. Or maybe also in some area there's a super shiny air channels inside, so where we see more.
Yeah, that's right. So let's move on to PointCab. PointCab is software that is specialized in sectional views, and I overlaid the point clouds from the Faro-Focus and the L2 again. And I generated cross sections and with the image resolution of 5 millimeters. And here I did some measurements of the highest deviations and did some screenshots, which we can see here. And most of the hall shows minimal deviations, so which wasn't I wasn't able to measure them because it looks like one line. And here are the highest deviations, and you can see here the highest deviation is up to 2.9 centimeter, and so we got the requirement of 3 centimeter absolute positional accuracy. Yeah.
Okay, perfect. So I think we can see in the below picture, there's one area. I can maybe task this here with my mouse. I don't know if this captured now. So there's one where you can see really a double line. I imagine that is maybe an area where we have maybe shiny material, because if you see the rest of the data set, it looks more similar. And I think if you have very shiny objects, I think that's not the best preference for the high sensor systems. So I think maybe this is the reason why we see a little bit double line on this area, but the rest looks super good.
Yeah, and I also analyzed the height deviation in PointCab, and they were not noticeable. So not even in the red marked area. Maybe if you watch the first video that we recorded, which was about the K1, the little scanner from XGRIDS, there we got some height deviations up to 8 centimeters in this red marked area. And therefore I did some sectional views in PointCab to measure if we got deviations, and we can see that not even in the problematic area we got deviations in the height. We can see it's one line, and yeah. So I also equipped the hall with reflective targets. Here, these targets. And the points outlined in green were included in the processing, while those outlined in red were used as checkpoints. And Lixel Studio features a function that automatically detects the reflective targets and compares them with the original coordinates. And the results show a horizontal accuracy of 1.4 centimeter and a vertical accuracy of 1.8 centimeter, what is a really good result. Yeah, so let's move to the auto accuracy analysis. And
yeah, maybe let me tell something. I was super interested in this, so because people are starting now using SLAM scanner for topographic survey, and we want to figure out what we can really achieve by doing this outdoor. So, and that was my idea, and so let us start.
Yeah, and for that I also used the reflective targets, and here we can see 2 screenshots from the outdoor area of the HTW Dresden. And on the left side we can see which crowd control points were used for the red loop here. That's the red loop. And the aim of the study was to determine how point cloud accuracy behaves under different configurations of GCP distribution. And therefore, I also used here these reflective targets, and we got 9 GCPs on our red loop. And the length of the loop is about 600 meters. Here we got the test 1, and therefore the GCP distance was under 100 meters. That's also the requirement from XGRIDS to achieve good data. And yeah, the GCPs used in the non-rigid processing were these one, and the checkpoint was the point 93, which we can see here. And it's located about, I would say, 20 meters far away from the GCP 164. And we can see that the checkpoint and the RMSE of the other GCPs are all under the 3 centimeter absolute accuracy. Yeah.
And for the METIF, we take the non-rigid. Non-rigid means that we give the software the opportunity to scratch the point clouds on the control points, so as that they can it's not rigid, so it's not fixed, so as they can move it on the right position. So that's where they say we can get better results out for the points between the reference points.
Here the test 2, therefore we got the GCP distance above 100 meter, and here on the right side we can see that I only used 4 GCPs for the processing. but we can see that they got a good placement. And here are the checkpoints. We got 5 checkpoints in this test. And we can see that the RMSE of the checkpoints and all the GCPs here are just minimal higher than 3 centimeters. So we also got great results.
Yeah, but I see in the horizontal accuracy we gone a little bit higher from 2.4 to 3, and for the checkpoint, I think. But in the high accuracy, they will jump from a 0.5 millimeter to 1.5 centimeters. So also 50 millimeters is 3 times more, and by the other ones is only 30% more. So I think there is something that we can, I don't know if you can say that, but from the points is that the high accuracy definitely increase higher. So I think we see it also on the vertical accuracy. So, but I don't know. This is only now our view here, or that's a general view. So it's pretty interesting.
So let's come to the last test. It was about a poor GCP distribution, and so that's how it shouldn't be done. We can see I only used the 4 GCPs here on the top. These are these 4, and we got also 5 checkpoints. And we can see that the RMSE of the checkpoints in horizontal accuracy is nearly 6 centimeter. And in height, we got really bad results. So don't place them like that. No.
Yeah, but this is a little bit, this is like what I see before in the other picture. That's now shows the same. So you have a bad distribution of your GCPs, that the vertical accuracy will be much more affected as the horizontal accuracy. And that's not now my if I see this data, but I think we only check some data. So, but that would be my short takeaway from this. But I don't know. It's a 100% science proved. But this is dangerous. So if you're speaking about topographic survey, I think definitely if you're doing street, I think construction guy can live better with horizontal deviations as with vertical. So as I don't do that.
Yeah, but we could say when we do it as XGRIDS says, we get good results also. Yeah.
Definitely. As everything what we're showing here in the end is not what the manufacturers provided. That's our testing.
Yeah,
Our
right.
practical testing. So we know people like cheating. So doing less than so because I'm under time pressure. So don't cheat.
No, don't do this. So let's come to the conclusion of the Lixel L2 Pro. The manufacturer's accuracy requirement of 3 centimeter can be met. And we got improved accuracy through the use of crowd control points. And the strengths of the scanner are the great absolute accuracy, we got simple operation, the efficiency, and the presentation of the data.
Okay, yeah, that's very good. I see from my point is what we saw also, it's like the need for GCPs to get high accuracy out. But what I really like on the newest generation of the SLAM scanner, if I know we are starting super early with the first GeoSLAM system, so the first development for practical use of SLAM technology with the Hukoyo scanner. I think to this point the point cloud quality was not them good enough to make any modelings or from that, and also the camera resolution to this time. Okay, we're speaking about 6-7 years in the past, so was not good enough for do many tasks of capturing buildings and topographical survey. We had other use cases for this system. So, but now with the newest generation, and if I see this one, I think there's complete change how you can use the system. So I think you definitely can capture buildings, and you can also capture topographical areas. If you use then ground control points, you can achieve a good accuracy. I would say so as conclusion. I'm right?
Yeah, that's right.
Yeah, I think we don't have to be complicated this to the end. So maybe to the audience, don't forget, leave a comment if you like to know more. So, and subscribe to the channel and give a thumb up if you like what Janis is doing for you. He spent a lot of time in that. So, and I can tell you, I was on this VDISG conference in Prague, and I met some of our YouTube channel follower, and they're speaking about our other accuracy video from the K1. So, and they say they like it. They say that's very professional done. So it's not. They see that we really spend a little bit knowledge and try to make it most scientific as possible for what we can spend at time for doing that. I'm right?
Yeah, sure.
I think even you speaking with your professor about our first results, so and make a little cross check with him.
Yeah.
Okay. So yeah, then to the audience, very nice. And I can tell you once, we are not finished yet. So we will bring more. Even that you can see on the picture, we have this instrument here. This system have also an integrated GPS, what we not was able to using yet. So I think the actual there is for Europe or for Germany, the complete transformation system and GeoEd system wasn't not ready to the point where we checked the system. So, and I think that's maybe something for upcoming testing, using then the GPS integration and check out what how a GPS integration can help us to working better with SLAM technology. Janis, you are happy to do it. So.
Yeah, I'm happy. We will move on, and maybe we get some new videos about the RTK.
Yeah. Okay. Cool. So then I say bye-bye. Also don't forget, subscribe to the channel, leave a thumb up. I say bye-bye, Janis, and thanks for your good work.
Thank you.
Okay.